Hi, everyone. Welcome. For those of you who don't know me, my name is Somaya Sadar. I'm the Assistant Director at the Center for Analytics and AI Engineering at the University of Toronto's Faculty of Applied Science and Engineering. Along with my colleague, Alex Olson, our Research Associate, we'd like to welcome our panelists for today's seminar on machine learning in practice for retail. Dr. Kanchana Padmanabhan is the Director of Machine Learning Solutions at Kinaxis, a global enterprise supply chain management software company. She holds a PhD in computer science from NC State University and teaches at the University of Toronto and Ryerson University. Kanchana is passionate about building productized ML solutions. Our other speaker, Anneya Golob, is Principal Data Scientist. She holds a MSc in astrophysics from St. Mary's University and is interested in demand forecasting and optimization problems. Today's session is moderated by Professor Elias Khalil, a scale AI researcher in data-driven algorithms for modern supply chains at the University of Toronto. I'd like to remind everyone that this session is being recorded. Please feel free to type your questions in the Q&A chat box during the seminar. And time permitting, we'll discuss the questions at the end of the seminar. Without further ado, I'd like to invite our speakers to start their presentations. Thank you.
Perfect. Thank you, Somaya, and thank you, Elias and Alex, for having us. It's always exciting for us to present to an academic audience because personally, we have a lot of collaborations in academia, and some of our best work and papers have always come out of there. So very excited to be here. So what I'll do is I'll just dive right in. So today we're going to be talking about machine learning in practice for retail. We'll give a little bit of an overview of this area as well as dive into some specific problems in the space and how we've thought about it and how we've solved it. And we'll wrap it up with some lessons learned in practice that that we've learned over many years of doing this in the industry. So hopefully it's useful for everybody who's attending today. Oh, sorry, Anneya, you're the one in control. So can you do the next slide, please? I think we can skip the speaker bio, so we can just go one over. Perfect. So for the agenda today, I'll introduce Kinaxis a little bit, what we do, who we are, and a little bit about the machine learning practice at Kinaxis. And then I'll dive a little bit into machine learning in retail space. What are the kind of areas that exist where machine learning can help? And then we'll dive into the demand forecasting space. I'll give a quick overview and then hand it off to Anneya, who will talk at length about all the problems that she's personally faced and while working in this space. And then we'll wrap it up with some other areas that we focus on, as well as lessons learned. So that's what we'll do. Next slide, please. So as Somaya said, Kinaxis is a supply chain system, a supply chain company. We basically have a tool called Rapid Response that helps with integrated business planning for both demand and digital supply chain. We have been rated quite highly by Gartner as a leader in this space. Kinaxis has headquarters in Ottawa, as well as we have offices in Toronto and India, and just generally sales offices and professional service offices all over the world. So our tool basically deals, if you can think about it, everything from raw material all the way to getting products into a store. So anything ML in this space we handle. So we were founded in 1984, so we've been around for a very long time, and we have customers in many different countries. We are also in over 7 industries, from aerospace to automotive to consumer products and retail to high-tech electronics and industrial. And many of the leaders in the space happen to be our customers. And in terms of AI and ML itself, Kinaxis has kind of gone into this space in the past, I would say about 5 years. But last year they acquired a startup called RubyCloud, which is where we come from. And RubyCloud has been in the space for over like 8-9 years. So we have a really rich history of machine learning work at Kinaxis. So I'll start with this slide, and I always like to throw this slide at the beginning of a data science presentation, because when I talk to people about data science and when I talk to students specifically, because I do teach many courses in these universities, I teach undergrads, I teach grad students, I teach continuing education students, I teach professional students. And often they all talk about the machine learning, the ML and the AI and the deep learning. And for me, that is, of course, really interesting and cool. But if you have to go into the industry and start thinking about machine learning, you're not just thinking about the modeling aspects of it, but you have to take a step back and think about, how do I get this model to my customer? Like, what does it mean that I take my prototype or my good research and then bring it to the customer so they can benefit, right? And that stems from building this entire ecosystem of things that can help you with that. So I just wanted to point out the different teams that we have and how we think about it, just to give you perspective of how an industry machine learning team can look like. So on the left, you basically have the data platform area. So data platform is its own discipline, own set, different set of people who effectively try to bring in data, whether it's customer data, whether it's other external sources like say Google or weather data, into our system and put it in a way that machine learning can actually make use of it. So this, if you can think of anything from say something as straightforward as ETL, which is by the way not straightforward. So something as simple as ETL to things like validations and things like schema management. And so pretty much anything data related and data quality related often falls on this team, and one of the critical parts to make a machine learning system work well. Another team or discipline I'd like to call out is this team that surrounds this box, which is the machine learning as a service, the MLAS team. So what they do is they effectively give us the platform on top of which we deploy our machine learning solutions. So they give us services to deploy our solutions. They give us solutions to easily scale our solutions. They give us all of the tools we need to say monitor our solution and so on. And so they effectively are the ones that help us make sure that everything machine learning is actually working well in production. And of course, the box in the center is where you might typically think of data scientists living. And there are, again, two teams here. There's data science team that does the research and the core solutioning. And then there's a machine learning engineering team that can take these solutions and then help us kind of productize it or write workflows and pipelines and make sure that these can be deployed on our platform and they can be run at some cadence, without failure. And if failure happens, they add in things to make sure that things can restart and run smoothly. So this box has everything that you might think about: feature engineering, training, forecasting, as well as if you have use cases, and we have a couple of use cases for optimization, which Anneya will talk about later. We also have an optimization engine on top of that to help us with some of those use cases. So hope this gives you a perspective of what machine learning in an industry looks like, as opposed to just thinking of it as modeling and deep learning. So anyway, Anneya, next slide, please. And I just like to throw this out there, not going into details, but we are very heavily involved with academia. We always try to have collaborations with them. We pretty much publish at least once a year with some academic collaboration. So if people are interested, especially professors, more than happy to chat because we're always looking to do some interesting problems. We can give you good data. We have a ton of it with lots of interesting problems, and you can obviously bring in your expertise, and we can do some good work together. So, all right, next slide, Anneya. Thank you. Next one, please. So in this section, I'll just briefly outline some areas where in retail, where machine learning can help, already helps. So it all starts with, there are two areas you can think of. So you can think of demand, which is effectively everything to do with once the product is in the store, how can you basically ensure that the customer is able to buy it and make sure that there's no loss of sales and things like that. And then the supply part, which is basically ensuring that the product actually gets to the store so that we can fulfill any customer requirements. So for the demand side, the most basic problem is, of course, the simple question of, what is the demand of a particular product on a given day? So that's a simple question that every retailer has. And there are some more advanced problems, like in terms of merchandising optimization, you can think of assortment planning, which is how should I organize my store in a way that I can maximize my sales? You can think of promotion planning. You can think of flyer configurations, like what should my flyer look like each week so that I can maximize either sales or revenue or some other metric. If I have an online store, then how do I do product recommendations better? And customer relationship management, like how can I ensure loyalty and prevent churn and things like that. So that'll be on the demand side. And on the supply side, of course, I have things like replenishment, which is exactly how much product should I send to a store on a particular time of the day. And how do I prevent things like stockouts where, I go to a store, but I don't find the product that I want to buy. So how do I make sure that things like that are minimized? Anyway, there's lots of problems. I don't want to go into too much detail, but this is the landscape. But one thing that kind of underlines a lot of these problems is this very first line that I put here, which is the day-to-day product demand forecasting. And if you get that right, you can kind of solve for a lot of these problems a lot more easily. And that's really the thing that we will be focusing on today. Next slide, Anneya. Just a couple of glossary things before we move on. We're so used to calling calling it this way that we wanted to make sure people kind of get it. The first thing is SKU. Anytime we say the word SKU, it just means product. Just think of it as product. When we say things like promotions, it's basically the offers that you see when you go into a store, like a buy one, get one free or a $5 off. Loyalty programs are, of course, things like air miles, where you sign up, you give your personal information that the retailer can use for targeting and advertising, but then in return, you basically get points and specialized offers and more benefits than other customers would. So just keep these in mind as we go along, because we kind of use them here and there. Okay, so there's lots of introduction that happen, but now let's just get into the meat of it all. So the question we really want to answer as far as demand forecasting or a day-to-day forecasting is concerned is the following. So as a retailer, I would like to know the demand for a SKU under some specific conditions. Of course, the word demand itself is vague, and Anneya is going to dive into what demand really means. But assuming that it is, some notion of how much, like how much the customers want a product on a given day, for example. So the problem just boils down to, can I basically give a number that denotes the demand for a SKU under some specific conditions? And those conditions can be anything from product availability to promotions that I want to run on a given day, to price of the product, to advertising, to maybe the geographical region where the store is located, to loyalty settings, to, frankly, the list is endless. The retailer can put any number of constraints on this demand and basically ask us, under these constraints, can you just tell us what the demand for the SKU will be? So that's really the crux of the problem. Next slide, please. And of course, on top of that, on top of the simple question, they'll overlay some additional conditions where they'll say, or objectives where they'll say, okay, give us demand, but then make sure that we don't lose out any sales. And what they mean is, remember the toilet paper crisis when people went in and could not find toilet paper? They never want that to happen. Like that is like a worst case scenario for them, where a customer goes in and then they can't find toilet paper or they can't find the product they want. And that means they basically go to the next store and start buying that product there, right? So that's something they really want to avoid. So that's basically called avoiding stockouts or avoiding sales. And typically that can be achieved by something like minimizing under forecasting. So making sure that your demand is not, the forecasted demand is not much lower than the actual demand. Another one is the opposite problem of that, which can also happen, where imagine that I'm selling salad packages and vegetables. If I end up overestimating my demand, then I would pretty much end up having to throw it out the door or my garbage many times, right? And that's basically money lost, that's it. So they really want to avoid that as well. So they also want to make sure that that over forecasting doesn't happen so that they don't have to throw things away, especially for things that are perishable. Of course, this basically boils down to having the perfect forecast, which is of course impossible. So it's always a trade-off on between under and over forecasting and working with your clients to figure out, okay, exactly what is acceptable for you. And, are you willing to live with a little bit more over forecasting? Are you willing to live with a little bit under forecasting? Where do you really land? So deciding that, and also obviously having the ML tools where you can actually tune for these things of under and over forecasting on your side to make sure you can exactly give them what they're looking for. And Anneya will touch on that topic as well. And of course, the last piece of it is they also want forecast for kind of any time in the future. So they can say, for one product, give me the forecast for next month. And for another product, give me the forecast for next Christmas. Because for a seasonal product, I only want to know the Christmas forecast. For non-seasonal products like, say, pasta, I definitely want to know how much I'll sell or how much the demand will be for next month. So it can be arbitrary. It won't be like a continuous, give me the next 6 months. It could just be arbitrary, just give me some time frame in the future. And the last one is they could also ask for forecast in different, what we call resolutions. And what that means is I could say, give me a forecast in a weekly bucket for a product. I can also ask for like a forecast in like a daily bucket. I can say, tell me the forecast for milk every day, but then tell me the forecast for pasta every week. And the reason they need this is how replenishment can work. So if they are able to bring in milk every single day into the store as needed, then a daily forecast helps them because then they can plan out when should their trucks come in every single day to actually bring product to the store. Versus if pasta can only come in once a week, then it's sufficient for them to know how much in the week they'll sell so that they can kind of plan at the end of the week, when exactly do I need the trucks to come in and bring in product. So anyway, so this is kind of some of the objectives that they have. And next slide, please. Of course, machine learning always starts with data. There's a ton of it. There's data sets that the retailers can give us, like transactions to start with, and then a bunch of other attributes that they collect. And of course, we also have external data sets like Google reviews and demographics and other APIs that we overlay on top of that. So this is definitely what you might call very rich data that we get from both the retailer as well as external data that we can overlay. And we also have, this is also truly big data because we get many years worth of data, and we can even get to the granularity of hourly if needed. So it's super granular and also super extensive. So truly big data. And the next slide. This is a very annoying looking slide, intentionally so. I put a lot of red lines here because when with big, what's the saying? With big power comes big responsibility. Basically, when you have a lot of data and you're given rich data sets, you're excited as a data scientist, but then it comes with a million problems that you have to deal with. And every single data set, except for maybe the transactions one, because transactions one usually comes from a POS system, right? You go automatically scan something gets recorded in a system, so that data comes from an automated system, so it's good. But everything else often has a manual component to it. There is a human either entering it into a system, creating it through Excel sheets, emailing it to each other, and that introduces a lot of different issues. Something as simple as misspellings that has created havoc for us, to something like just missing like data, just people just forgetting to send their files in, and that just creates artificial gaps in our data that we are never able to reconcile. So there's a lot of problems, and in the data itself, I'm not going to go into the details of each one, but just know that typically the secret sauce of any company that deals with these kinds of problems is in the data. If you have a good strategy to deal with your data, and if you get the data to a good quality, it can almost guarantee, for the most part, a good output quality for you. So focus on the data, spend a lot of time with it. That is really where the money is. So, okay. Next slide, please. Now that I've set it up, the problem, the data, I'm going to hand it off to Anneya, who's going to walk you through one of her favorite topics, by the way. What is demand? What does it mean? How do we model it? So Anneya, please take it away.
Thanks, Kanchana. So yes, as Kanchana said, every problem that we can apply machine learning AI techniques to for retail pretty much requires that we start with a forward-looking forecast for demand. But when we get down to it, what that actually means we're trying to predict is very, very fuzzy. So when we receive data from a client, typically it's in the form of individual transactions. So basically what you see on a receipt when you go and buy stuff. And we can think of that as observing demand events where we registered a successful realization of someone wanting to buy something. Lots of different time series analysis techniques where you can think of those as being generated from some distribution, and you can do things like predict the time to the next sale. But typically for our purposes, we're not really interested in that. So we look at a more aggregated view. So this is a lemonade stand, let's say. And once we aggregate those individual sales to hourly, let's say, we end up with possibly some holes in there. So for the first hour, we can say 1 lemonade was sold, the second hour was 4. The third one, a huge question we have to face is, do we want to say the demand was 0 there? Is that something we want a model to learn from? Do we care whether a model is able to predict that 0? So most of the time, it's not a good idea to throw a 0 on there. For a meaningful 0 to occur, we need to be very, very confident that any customer who wanted to purchase lemonade at that time was able to do so. So that means the store was open, it was staffed, people could get there, they had enough lemonade, and so on. So just the sales data is not enough to determine that. We usually want to compare that with inventory, store hours, whatever else might be happening in the world at large. But typically, we try to avoid that at all costs. So yes, like I said, we end up with a time series, kind of, but it's typically not contiguous. And there's a whole other can of worms we could open when we say those places where that 0 could or could not be filled in represent right-censored measurements of demand, but there's no reason that any of the other time buckets we're looking at aren't right-censored either. Can we be confident that in that hour where we sold 4 lemonades, we couldn't have actually sold 5 and they ran out a quarter of the way through? So that's typically not as bad of an issue, but something we do think about a lot. So in the end, we end up with data where we have big holes in it. So a lot of time series methods that you might think are the most intuitive solutions to apply are not really a great choice. Really, anything autoregressive, we try to avoid most of the time so that we don't have to make unfounded assumptions about the data there. So to that end, we typically end up with some nice tabular data where we have some start and end time that represents the period where we're aggregating demand, hopefully across. And we have features that represent properties of the SKU or product, things about any promotions that are applied, whatever attributes we found from external data sets, try to capture some seasonality, whatever else, and some value that we're trying to predict that hopefully represents the total demand in that time. Setting up the problem like this naturally allows us to train a model on everything at once and exploit commonalities between different products and stores and whatever else, using categorical encodings and stuff. But since we're not using any explicitly autoregressive features, we need to add some tricks to capture all of the effects that we would otherwise be able to automatically. So to do that, we borrowed a lot of code from the Profit library. We use the Fourier sums to represent different seasonal orders and just add those in as features. We can also deseasonalize the data and fit some sort of trend that we can extrapolate into the future to create some meaningful trend features. In the absence of that kind of trend fitting, we can also use models that can accept different sample weights during training, and we put more emphasis on recent observations so that we can still fit seasonality over several years, but understand that the near future is most likely to be like the recent past. And interesting thing there that I don't think I really saw coming was that the kind of extrapolation and trend fitting that we put a lot of time into is often very, very unwanted by clients. So sometimes like we have a nice trend going and we send a forecast and they say, what the heck is happening? I never ever want to see a forecast that is above the 95th percentile of a historical distribution. So that if that is the case, it makes our lives a lot easier and we don't have to deal with any of these kinds of trends. So we usually go with the weighting method in those cases. So I guess I didn't explicitly say, but we are, in the absence of those autoregressive features, we're treating our data sets as independent and identically distributed, I can't talk today, observations, which let us use any regression supervised learning technique out there for the same data set, which is really, really nice. So we don't have to make any assumptions about these no observed demand instances. We just get rid of those records, not that they existed in the first place. We also have the option to just throw out chunks of historical records that we don't want a model to learn from. So that often means things like pandemics, or we've had big issues with E. coli outbreaks in salads, where you end up with things being missing, and then that shifts demand to different products. And it's just not good to teach a model from that. So we have tons of different options for algorithms we can throw this at. We can use pretty long histories like this. We can trivially change the forecast horizon. If a client says, tell me the forecast for next week, or tell me the forecast for 2 years from now, we can use the same feature set to generate that because we don't have any explicit autoregressive terms. I guess this is more about the models we use, but we try to use things where we don't have to pre-sort features and get rid of anything. We just throw everything we need at the model. That typically means boosted models. And with this, we get everything done pretty quickly. I think it's a very good system. So I talked about the data and models a little bit. Obviously, we need to do hyperparameter tuning before we start throwing forecasts at clients. So whatever model we choose, there are definitely some parameters that need to be set to control the learning process that can't be learned during training. So since we do have time series-ish data, we need to be careful about setting up cross-validation during that tuning process. So as you can see here, we try to pick multiple historical periods where we can get reasonably long training and test sets, where we can test different combinations of hyperparameters and see how they perform on different holdout periods. So this gets a little bit tricky. Typically, clients can give us maximum of 5 years of historical data up front. And really, a training period less than 3 years is not going to be enough to really be able to capture any seasonal patterns. So we have to be really careful about selecting these cross-validations periods reasonably. 3 years of data or bust. Lots of different techniques that we've tried. Recently, we're very much into the Optuna library that provides implementations of lots of nice algorithms and really good interface. Another interesting thing there is that the objectives that clients want to set during tuning and training are often not well represented by a single metric. So they typically want accurate forecasts, obviously, or maybe slightly over or slightly under. As Kanchana mentioned, if they're very cautious about missing sales, they might want to over forecast all the time or so forth. And they also, I think, sometimes are very focused on metrics that are not symmetric, and because there's a lot of zeros in these data sets often, basically not great metrics. So they really like WMAPE as an objective, which if you just optimize for WMAPE we basically end up under forecasting across the board. So we really want to be able to tune for 2 objectives or more simultaneously. So we've put a lot of effort into making sure we can use multi-objective optimization techniques during hyperparameter tuning, which allows us to explore the Pareto front of different sets of hyperparameter combinations. So typical example would be we want to minimize both error and bias, and we set up a system where we explore different sets and we don't know anything about the relative importance of those two during this process, but we can explore this whole front, return this to the user, and they can pick the best set of parameters that they feel gets the balance between the 2 objectives right. So another hugely important thing that clients really want in a machine learning system now is explainability. So black boxes are no longer acceptable. They need to know the why of these forecasts so that they can develop trust in them, and often they want to use explainability. No, did not click. Explainability to make business decisions. So typically we use tools like SHAP to provide explanations of each individual prediction. And either SHAP-based or other feature importance to explain the overall behavior of the system. And final thing I'm going to talk about is the problem of future revenue. So once we have an estimate of future demand from our system, we want to also think about what that means for revenue. So the total revenue that a SKU will generate in a given time is the predicted number of units they're going to sell times the sale price, the average sale price of the item. And you'd think that that would be a pretty easy thing to do because we know the price of the item in the future. But it's actually a lot more complicated than that, because with loyalty programs and different promotions, often there are like definitely more than one promotion applied to a product at any given time. And there are seniors days and student days where there's just random 15% off discounts, and no one is ever really required to avail themselves of any promotion available to a thing. So we typically build a model that takes in all of the promotional conditions around a product and use that to predict the average price that people will pay, which allows us to multiply that by the demand forecast to get an estimate of the predicted revenue. And one example that I still find fascinating is the way people respond to different types of promotions psychologically. So this is time series plots of daily sales of 5 flavors of a salad dressing. And so on the left, there's a straight 50% off regular price promotion. And you can see there's like a little boost in demand, but not crazy. And then when they do a buy one, get one free a few months later, the boost in demand is like a factor of 10 greater. But in the bottom plot, you can see people are actually on average paying more for an individual bottle of salad dressing. So buyer beware, I guess, or have more BOGOs. So now I will hand it back to Kanchana for a quick discussion of new product and store introductions.
Yeah, so Anneya kind of, she almost summed up a lot of our pain points into a few slides. Like, these are not things that we woke up one day, started this area and said, this is how we're going to solve it. It's just things that we've gone through a lot of evolution. The first models that I implemented for the space were some time series problems with some linear regressions and with some random forests or some ensemble. That was literally the first setup that I had. But of course, we soon learned that as we looked at the problem more, we're like, oh, these assumptions don't make sense. And this is kind of having this unintended effect of too many zeros. Suddenly we're under forecasting like crazy, and it really isn't meeting the demand, and we're basically not giving the client what they want. So we've gone through this entire like many years of this is how we'll do the problem to like, oops, no, this actually doesn't make sense. Let's dig in a bit more. Oh, we have this other client data that's teaching us a bit more. So we've done, I think, I don't know how many pilots and implementations we've done in all these years, but every single data set teaches you one additional thing about, oh, this is something we didn't think about, and now we have to think about it. And this whole revenue question is like a huge question, because often customers simplify it to, oh, you have a promotion, just take the discounted price and just multiply. That'll be our revenue, right? And then when they get the actual numbers, they're like, oh, but this doesn't make sense. Like we made more or less than what we thought. And we're like, no, but the reason for that is I could go into the store and not avail a discount. I could take my mom, who's a senior, and then she might avail a discount that I don't have. Or I might just choose not to buy. I'm not going to buy 3 pasta sauces and keep it in my house. It's a waste. So I'm only going to buy one, no matter how much you try to sell it to me. So it's very interesting that these problems exist. But the good part about ML is we don't have to explicitly manually deal with it. We can model it in a way that the machine learning can understand these patterns, and for us not to have to put that. So anyway, it's very fascinating for me to talk about it because we've done it long enough. Anyway, so now that Anneya's talked about the machine learning aspects and what we think of demand, how to model it, how to tune for it, and what are some secondary benefits like explainability and average price modeling that we get as a result of it, I want to open it up to a few more areas that, this modeling, the way that we model has really helped us solve for. I'll talk about the first one, which is a new product and new store introductions. And then I'll hand it off to Anneya to talk about the 2 optimization scenarios we have. One is the scenario planning, and the other one is the true optimization problem that we've solved for. Next slide, Anneya. Okay, so this is a really extremely tricky one, and something that the customers very rarely know how to solve well. So this is the case when, when they introduce a new product or they open a new store. So this one's a personal favorite of mine because it was a personal pain point that was solved. So Tim Hortons is actually the nearest store to where I work, where we work, but they didn't have matcha latte there for the longest time. And so I would have to settle for a green tea or take the hike to Starbucks that was all the way across the street to actually get my matcha latte. So I was really excited when they introduced this. But of course, as a data scientist, the question is, okay, I introduced this product, and the customer will say, okay, now tell me what the demand for this product will be. There's no history. There's very little information about it beyond maybe the product attributes or something like that. And then you're like, okay, like figure out a demand. Or the same thing could happen at a much larger scale when they open an entirely new store. And I saw this recently in the ad, I think it is an October 2021 ad, where they said they're going to open a new store. Starbucks is going to open a new store in downtown Victoria. And then you have the store with all of these million products. And then you have to figure out how much is the demand for croissant at that store on Sunday of, like, I don't know, January 1st or something like that, right? Like the question is, how do you know what it is? And often I think a way that retailers go about it is, and I've seen this quite commonly even elsewhere, is they'll say, okay, let's find some matching products, right? Like let's find a product like this product or a store like this store, and we'll try to maybe use that history explicitly. So either we can say matcha latte is like green tea. I personally disagree, but let's assume that that's the case. And we'll just say, let's use the history of green tea, and then we'll kind of build a model and to predict the matcha latte's forecast. Okay. But the problem here is, of course, the manual effort. Like how do I even find these products, and how much do I have to sift through the data to find them? And the second one is just knowing what a good match is. Like, how do I know green tea is a good match for matcha latte if I have like no, and should I only be using one product? Should I be using green tea and another product? Like, exactly what should I be using to get a good estimate for matcha? So next slide, please, Anneya. So because we think about it as IIDs and a machine learning problem, and Anneya alluded to it when she talked about the benefits, is we can group things together. We can basically maybe throw all of the teas, or all of the coffees together, for example, into a machine learning model, throw in a lot of different features about the product. Like we can have embeddings, we can have explicitly encoded features, we can have, features that come out of your, deep learning models, not for forecasting, but just for like, a feature representation, like a product representation, and then throw all of that into our machine learning setup, and then let the machine learning do its job, which is the machine learning, if it finds similarities, will naturally try to group products, and then you can still get a forecast for a net new store or a net new product that way. This has typically worked pretty well for us, and it's definitely better than finding a one-to-one match or explicitly picking out cherry-picking products or stores, which is usually very hard, and often you'll probably do a bad job. So, we throw it at ML, we formulate it in a way that ML can solve it for us, and that's worked out pretty well. And Anneya, next slide, and you can take over.
Okay. So another huge thing that we have built thanks to client demand is these different kinds of tools to help retailers optimize their promotional plans. So the first one is a what if scenario builder. So I think what I alluded to before is that we have this batch forecasting service where retailers can upload their future plan. They tell us what the price of everything is going to be, what promotions are going to run, what's going to be made available when, and we weekly, monthly, whatever, spit out a forecast for the next year of demand for everything. But here we have basically a different entry point to the same inference service where on the fly, users can create a hypothetical promotion and generate forecasts that correspond to things that belong to it. So in that way, they can compare different scenarios of different promotions. Say, if I made this a BOGO versus if I made it a 50% discount, what would the impact to my business be? And they can build those promotions there and then feed them back into the system that they use to run these things in practice. So this is really possible because we are assuming that the data is IID. So we don't have to generate features that cover the gap between today and when they plan to actually run this promotion. We can just take what we need on the fly and feed it into the same model that we trained on historical data. This is really popular amongst retailers, perhaps even more so than the second thing I'm going to talk about, which is kind of unintuitive. So we also have a real optimization engine where, because we are treating all of these forecasts as independent, we can say, if you give us a set of hypothetical promotion types that you're considering for the future, we can generate an exhaustive set of forecasts for every possible combination of products in every possible promotion for the future, and then set up something like an LP to solve for the optimal plan in terms of total business revenue or total sales or whatever else we want. So this is a really fun problem to work on, and you really learn more about how retailers work when you let them set up constraints on these kinds of optimization. So they have a lot of rules, like in the flyer, we can't have a picture of cereal from this brand next to milk from this other brand for political reasons or something. Lots of stuff like that, lots of rules about the cadence of promotions on different things, the maximum discount they're willing to consider, and so on. But yes, so we have the ability to do that, and it's a really good system. And finally, Kanchana will explain a bunch of lessons we have learned.
Feel free to jump in, Anneya. So yeah, we actually sat together, we were like writing down things that we want to call out as lessons learned, and we cut it down because we're like, okay, we need to fit it into a slide, and we'll try to point the main things out that we think people will benefit from, as opposed to just ranting our personal issues. So the first thing is, of course, the biggest lesson for us, or actually all of them are pretty big, but to start with is tree-based models and probably what you may call simpler or normal machine learning systems or models typically outperform neural nets and deep learning models for us, especially when you think of the forecasting problem itself. The way we think of deep learning or models is, they can help with things like feature engineering. They might get you good representations for products or good representations for stores, but having to use them to do things like forecasting is often not necessary. And tree-based models really work well, both in terms of just getting good forecasts out, but also in terms of ease of deployment, ease of training, making sure that when we hand it off to a professional services team that's going to deploy to a client, they are themselves able to use it, easily. Tree-based models definitely in terms of like for pure accuracy, but also in terms of how easy it is to like throw a model like that into production and make it usable for a product. The second one is a huge one. Your time is better spent fixing data than building fancy models. It's something that we've learned over the years. We've done it. I teach a full-on course on deep learning at Ryerson, the master's program. And I always tell them all of this is good. And when the right use case is there, they are hugely beneficial. But then at the end of the day, garbage in, garbage out. So if you're not going to focus on your data, the output that comes out of it is not going to be useful. So spend time with your data. It'll really give you that huge like jump of benefit when you're getting your results. You can no longer get away with black box results. I think everybody agrees. I think there's been a lot of conversation about it in the recent past. Explainability has to be at the center of your solution, whatever you build, even if it's your class project, know that adding that piece in will kind of change the tone of any result that you're providing. So definitely put it at the center of your project. Retailer data, technically, I think we've dealt with a few different verticals. So I would say in general, data in the industry is broken simply because they were never collected to be in an ML system, right? Like if a retailer knew it was going to be in a machine learning system, he would have done a lot more and a lot more things better. But it'll always be broken. The best you can do is work with them so the process going forward is set up better so you can start collecting better data going forward and kind of inform them and tell them, here are the places where your data is broken. And this is what we can do now. But if you start doing your practices better, in 2 years from now, you would have already had 2 years of good history, which you can kind of catch up. So definitely that's another piece to think about. The next 2 points are things that I personally like and I think we've experienced is a retailer improving their own data sets often gives you a much more improved performance than trying to keep throwing in lots of external data sets. Often there's a lot of marketing around weather and flu and let's throw this in and that in. But if your core data is broken, this stuff doesn't matter. So your standard data will give you the most benefit and external data sets can give you deltas. And they might solve some nuanced use cases where it's not captured in the standard data. But if this is bad, then this external data may or most likely won't kind of help you a lot. And the last one is definitely the distinction between online retailers and brick and mortars. So when you think of retail itself, there's a lot of different divisions that you can think of. But a big one is just when you think of online retailers versus brick and mortar, your brick and mortars, the online retailers obviously have a very different way of collecting data. They have everything online, everything set up. They can get customer data. You can get, product data is a lot better. You can think of other problems like purchase intent and things like that to solve. And product recommendations become important. Versus when you think of a brick and mortar store, you're thinking of things like stockouts and you're thinking of things like, promotional effect, but promotional effect in conjunction with another store nearby that has another promotional effect, for example. So the problem you deal with are different. And often a retailer may have both, right? Like a Walmart or any person that you take, especially in the pandemic, has developed an online presence as well as a brick and mortar. So treat them separately, treat them as their own things and kind of deal with them separately and not group all of them together. So I think that's it. Like, I hope this was useful and informative. And the last thing I want to leave you with is we are hiring. We've been hiring like crazy for a while now. I have positions on my own team that are open as well as other teams, machine learning engineering positions, data science positions. There's positions on the machine learning as a service team that I talked about. So if you're interested, please do reach out. Happy to have a chat about it. So Thank you very much. And thanks for having Anneya and me over again.
Yeah, thank you very much.
Okay, great. Thank you both for a very interesting talk. So I have some questions, but maybe first we'll start with the ones in the chat and the Q&A box. So Surav asks, what are some of the data quality assurance metrics that you would suggest in the context of retail industry? And I think this is in the slide where you're talking about how things can be kind of less clean than you'd like.
Yeah, so you can, Anneya, do you want to take this one?
Sure, yeah. So it's very hard to standardize because, like to write some sort of standard set of checks, because typically the point of sale systems that retailers have to generate these data are bespoke systems set up by some companies. So there's no industry standard input format. But the things that we do run once we have things transformed into some kind of useful data model is to check things like when they give us, a start date, end date, and a price for a product, we need to check that there is only one. We need to check that there is a price for every product at all times when they tell us it's going to be made available. So typically, we need to figure out the pattern of how we're going to join all of this together to get final features to feed into a model, and then we can run these types of checks to make sure there is a value for everything that we've said needs a value. But from a retailer side, I'm not really sure what to recommend other than like centralize the data collection system, and then that would go a long way, because a big problem is that in brick and mortar stores, even if they're feeding data into the same system, it's manual entry typically, and often different managers of stores will use different fields to capture data. Like there was one terrible example of someone who put 9999 as a value in an inventory table as a note to self to reorder, which was a terrible situation. So for companies to make sure stuff like that doesn't happen would be a great start.
Just to add one more thing to that is, from a perspective of a company that needs to ingest this data, I think the biggest thing you can do is any metric that you can think of, like whether it's as simple as null checks to the checks that Anneya is talking about, and make it visible. Like usually as a data scientist, when I'm developing a product, I'm not the one deploying it for each client. I have a professional services team that's actually, who are the data experts, who are just going to go and get the data from the client and make sure that it's ingested properly and usable, to make sure that they have an interface where they can see all this information and they have opportunity to either do the fixes themselves, or they can go back to the client and say, hey, here's a report. We typically generate a report called the machine learning assessment report to say, hey, these are the issues in your data. And while we can still run with it, like we can definitely generate a forecast, but if you fix these issues, this is the benefit you're going to get. And that's just basically from our past experience. We kind of talk about what the benefits are. And then either they choose to fix it, or they can say, oh yeah, sorry, like this is literally data we cannot get, or this is like a huge process change. And you can imagine in a company, a process change means a lot of work to get it done. So, and it's also about visibility. So it's definitely about what Anneya said, but also about making sure that they know that this is the situation with their data and a clear assessment of what their data quality is.
Okay, thanks. So there's a question in the Q&A from Samin. Do you use something like sliding window splitter for cross-validating time series in which the IID assumption is violated? So I think this was part of your presentation, Anneya, about how you turn this sequential problem into a simpler IID problem.
So we definitely do use a sliding window for cross-validation, but then feed that data from each fold in as if it were IID. But we maintain that ordering so that the metrics we get during tuning are still representative of what a model could have known. I guess technically, if we didn't use that sliding window to generate folds, it wouldn't really be cheating in terms of machine learning if you're trying to generate a forecast for the future. But because whatever you're seeing in the history represents the retailer themselves learning lessons and saying, I did this promotion in the past and it worked well, so I'm going to do it again in the future. You want to maintain that ordering so that you're not inflating any metrics.
Okay, that makes sense. Thanks, Anneya. So Mohammed asks, have you used tools that combine simulation techniques with ML algorithms, for instance, for what-if analyses? If so, which simulation software have you utilized?
So I think the answer is no. I'm not sure what we'd be simulating, I guess, individual sales if that was what we wanted to, but typically.
I guess the machine learning model is doing the simulation for you.
Yeah.
Exactly.
Yeah. So we like our well-trained forecasting model is all we need to compare these scenarios.
Yeah. And the simulation is typically because it's a real-time system, it's almost interactive by the end user. So they can run a bunch of different scenarios and they can just look at what basically is happening. And if and basically that gives them the input of, do I want to run the promotion today or should I just wait until 2 months from now to run it because it seems to give me more benefits? So that's really the level that they need and that they find useful. So.
Okay, and so Maya, I guess we have maybe time for one more quick question. So Yun Cheng asks, for the modeling, is a skew treated as one of the features, or should we use categories and subcategories instead? Since if you do a one-hot encoding, you get a very large dimension in the representation.
Yeah. So usually, it is a very important feature when we're treating this data as one giant set that we're sending to a model together. So we definitely want to keep it in. Typically, we use label encoding rather than one-hot encoding and use a boosting model that can accommodate that. I think right now our go-to is LightGBM. Typically, it does a really good job with pre-splitting on categorical features, so we don't have to one-hot encode. But the subcategory category thing is also interesting. We include those when available as model features as well, also label encoded. And then for a given retailer, to train a single model for the entire universe of products is usually unfeasible because it's very, very big. So we treat the data in segments where we cluster together all products that share commonalities that would be useful for forecasting, which helps with the cardinality of those categorical features.
Okay, great. Thank you both for your answers. I think in the interest of time, we're gonna have to wrap it up here, right, Sumaya?
Yeah, I guess so. Thank you very much. This was very interesting. I personally enjoyed it, learned a lot. I'm sure everybody has, and I see a few more questions. It's very unfortunate that we have run out of time, but hopefully these discussions would continue in the future, as Kanchana mentioned, with more collaborations with academia down the line. Yeah, I'd like to let everyone know that we have a few other seminars planned for the new year. So make sure that you visit our website and subscribe to our email list or just follow us on social media and just stay tuned about them. Thanks again. This was really great. Appreciate it. Thank you.
Thank you so much for having us.
Thanks so much.
I really enjoyed
Thank
it.
Thank you, Kanchana and Anneya.
Thank you.
Take care.
Bye.
Bye.